Thank you so much, Dawn. Can everybody see my screen and hear me okay?
Sounds good, looks good.
Excellent. Thank you everybody for sticking around to the end of the day and the end of the workshop. All of the presentations today have been so great, so I'm really happy to be a part of this. And just looking at the time, I'll try to be as efficient as possible here to wrap up not too much overtime. So I'll be talking today about our recent work on the subsurface influences of watershed nutrient dynamics in an agricultural system. Just as a bit of a background, we know that in southwestern Ontario, there's still ongoing water quality issues, in part due to agricultural activities that lead to excess nutrient losses from fields, despite management and monitoring efforts. It's really tough because there's complex interactions that occur between the different hydrologic compartments and climate conditions that affect how nutrients stay and move within the watershed. There has been increased recognition for the need of groundwater surface water monitoring. For example, in the recent COA, the Canada-Ontario Agreement for Great Lakes Water Quality, they've identified groundwater surface water interactions as an area of focus. There's also a need to explore how different methods work in different settings for groundwater surface water assessment. So in clay settings, such as this one, it's sometimes difficult to capture the interactions on smaller scales. So different methods to identify the interactions is good to know, especially since those interactions may occur. For this study, the main objectives are to evaluate the influence of subsurface conditions on watershed nutrient loading, identify the seasonal variations of groundwater surface water interactions and tile drainage activation that affect nutrient transport from field to surface water, and to develop a conceptual model that describes the seasonal variations of groundwater surface water interactions and nutrient movement in this clay plain watershed. To achieve these objectives, we sampled for nutrients and stable isotopes for multiple groundwater and surface water locations within the study watershed. The study watershed is the Upper Park Hill watershed in southwestern Ontario in the Asaba Bayfield Conservation Authority. It's mostly agricultural fields, with 75% of those fields tile drained. Um, Sampling and studying the watershed started back in 2016, so there's been a few different modeling and monitoring papers and presentations, I think a few at this workshop in the past couple of years, but I'm just focusing on our recent work and publication in this for this watershed. To look at the Burgundy squares, so the A to Q sites are surface water sites, and they were sampled on an event basis, so just a couple times a year for nutrients and isotopes. The red triangles and black circles were sampled monthly, and the red triangle sites are surface water and groundwater sites, so they have monitoring wells adjacent to the stream. In the upper part of the watershed, the sites look more like this. So right against the fields, this one actually has a pretty good buffer compared to some of the other sites. Whereas when you get into the southern area of the watershed, there's a lot of forested area and bigger buffers between the agricultural sites and the surface water. This is an example of one of the groundwater and surface water monthly sites. So there's two wells adjacent to the watercourse that we would sample. All the wells are about 16 and 6 meters below ground surface. A lot of the sites also have dry points either in the bank or the stream. On the left, we also used data from an integrated water and climate monitoring station. So this was developed back in 2012 at a Water Survey Canada station. So over 10 years of data now. They also have 28 different sensors that measure surface water, groundwater, soil, and climate. We also have, we call this the edge of field site. All the sites are at the edge of a field, but this one has increased monitoring. So we looked at soil, There's a bank drive point. We monitored a tile outlet and the stream flow. We did have continuous water quality and drive points in the stream, but we had some damage and theft issues, so that data was unfortunately not part of the study. Like I said, sampling started back in 2016. So a lot of different parameters and analytes were sampled from the various groundwater and surface water locations. This study will just primarily look at total phosphorus and nitrate in the surface water and then stable isotopes from surface and groundwater. Um, I don't know if this will help make anything more clear because there's a lot of different sampling campaigns going on. But for the first objective, we looked at the watershed as a whole and the surface water nutrient exports from that integrated station. And then we looked at how that correlated with subsurface parameters. And then for objective 2, to look at seasonal groundwater surface water interactions, we looked at the watershed-wide sites for nutrients and isotopes. And then for objective 3, we tied together for a conceptual model for the surface water and seasonality of water inputs and nutrient concentrations. For the nutrient loading calculations, we had samples from the integrated station. Um, so we had our monthly samples, we did some supplemental event manual sampling, and we also had automated samples for the events that the Asaba Bay field collected for us. So we were able to capture 75% of the events over 2 years. So that was about 86 samples in total. As a summary for the monthly nutrient loads, we had two peaks. So in March of 2021 and February of 2022, we had the big peaks from big snowmelt and rain on snow events. And then this September 21 peak was from a really intensive summer precipitation storm. In June and July of 2021, we had increased nitrate loading, but not really the same increase for phosphorus. So that was mostly driven by increase of just low precipitation, low intensity precipitation events that summer that drove some of the nitrate movement in the watershed. When we looked at correlations between the monthly precipitation and monthly loading, there wasn't actually anything significant there. So we looked at other drivers, so such as subsurface parameters to see how those matched up with the loading. So for nutrient loads in groundwater, there was a slight relationship between nitrate and the groundwater elevation. The green dots are the growing season and the black dots are the non-growing season. So there wasn't a significant difference, but a slight pattern in the growing and non-growing seasons. And then total phosphorus, there's no relationship with groundwater. Looking at soil moisture, so we looked at depths of 10, 20, and 50 centimeters. At 10 and 20 centimeters, there was no relationship between nitrate or phosphorus loads. But looking at 50 centimeters, there was an increased correlation with the nitrate loads and an even higher relationship with total phosphorus. And then looking at tile flow and nutrient loads, there was a strong relationship with both nitrate and total phosphorus. And that's just highlighting the importance of tile flow on nutrient movement in the watershed. To look at now the A to Q, so the whole watershed-wide sites that we sampled for nutrients and isotopes. We did that sampling in June of 2021, and then we did the sampling in June 28th, which was after just a low-intensity rain event. The nitrate concentrations in the surface water increased by 300%, so there was lots of nitrate movement from that event, but the isotope signatures didn't really change. Looking at the hydrology of that event, so the tiles did flow, but there was no impact on groundwater or really soil moisture. So that's maybe just highlighting that that movement was really from recent precipitation and recent nitrate inputs in the watershed. We sampled everything again in April of 2022. So this was just base flow conditions, so it wasn't following snowmelt or a big rainfall event. And the nutrients weren't elevated, and the signatures were very similar to the average groundwater signature. The groundwater levels were elevated at this time, so this could just suggest that in this time the groundwater was connecting to the stream either through a direct connection or just through the tile drainage. Results from the edge of field site showed elevated total phosphorus and dissolved reactive phosphorus in the stream, but not really in any of the groundwater locations. And for nitrate, the tile had increased levels of nitrate, and as well as the stream. It was also very seasonally variant. So just looking at the objective 2 of looking at seasonal changes of tile flow and how nutrients are transported, looking at the isotope data, which is the purple triangles, we can see that it changes throughout the year for our samples. Closer to the summer, they're possibly following the precipitation trends with even a bit of evaporation. And then closer to the fall and winter, they're closer to the groundwater signatures at that site. We didn't get into much further isotope analysis, so next steps for this would be to either look at a mixing analysis or hydrograph separation for either the tile flow or stream flow to really look at some of the differences and contributions. Just some final thoughts and bringing everything together in the conceptual model. So we found that subsurface hydrology does play a significant role in watershed nutrient export. Tile activation mechanisms could be seasonally variant. In the non-growing season, we had decreased nutrient concentrations, but increased nutrient loadings, as well as possible increase in groundwater contributions to the surface water, either through the tile or a direct connection. And then in the non-growing season, we had increased nutrient concentrations with decreased loading and less of a groundwater contribution to the stream flow. Thank you, everyone that collaborated on this project and all the co-authors on the paper. Yeah, thank you so much for listening.